please.
Yep.
Usually we don't have to press it, and I'm just like,
Yeah.
what is going on?
That software is cursed. Like, you've got to know that now, right?
I know.
It's kind of like the SLS, where, first
No, it works
launch,
way
then
better
it gets
than
rolled back into
SLS.
the back.
This is the space shuttle.
know.
It still leaks helium, still leaks hydrogen,
Dangerous.
rather, but
Very dangerous.
it's your grandpa's pickup truck that you can mostly trust.
But it does get you off the ground from time to time.
I have Nancy's confirmation that all is good.
Okay, good. Good. Man, so we had fly overhead just 5 minutes before we got started. I guess they summer in the Arctic or like northern British Columbia, and then they fly back down south down to like, I don't know, Mexico, Costa Rica, and they go in these giant groups of 50, 100 cranes, and they're a big bird. Like they're the size of like a great blue heron or like they're a giant bird, and they all make this noise, which I will not attempt to mimic. And it's just for about 4 hours, it's just fleet after fleet of sandhill cranes going overhead. It's quite astonishing. It's amazing to see.
I've seen that with snow geese in a place where they go for the winter down south, almost to the border. And there's like 100,000.
Yeah. Oh,
That's
very cool. It's amazing.
And swans actually look kind of ludicrous when they're flying in big flocks because they have necks that just simply go on forever and ever. And to see these, there's some years we get as high as 100,000, but usually there's just tens of thousands of swans where there's a levee up in the river and a hydroelectric dam, and the hydroelectric dam keeps the water from freezing over, so things love to winter over right there.
Yeah, we had Crew Dragon just fly over us here. Speaking of flyovers.
Oh, good.
That's
cool. I managed to see it. It was moving pretty fast. It's still in lower orbit, so I was racing back in here to get on the show right after the pass, but I wanted to see it. So
yeah.
Well, I just watched
All right, let's get started.
Falcon 9 launch. A few
yes,
minutes.
they did 2 launches today. Those were the closest.
Crew 5 and was it a Starlink?
Another Starlink from Vandenberg.
Starlink.
Yeah, but this was the closest spaced in time that SpaceX has done, like 2 launches in 7 hours.
Yeah. All right, let's get started. Hello and welcome to the Weekly Space Hangout for Wednesday, October 5th, 2022. I'm Fraser Kane, the publisher of Universe Today. This week, we're going to be talking about globular clusters, gravitational lenses, Juno's Europa flyby, the solar cycle, and where did Ryugu come from? Joining me this week, I've got Dr. Pamela Gay.
Hello,
Dr. Gay.
everyone.
How's it going? Why are you on camera?
So
what's going on?
Apparently, there was another scheduled journalist who just couldn't quite make it this evening, and since I was already going to be sitting here with y'all, Nancy asked me to be on camera this time.
Yep. Awesome. Well, thank you. And engineering. So just keep that in mind, that if Pamela's brain seems a little distracted. Oh. Yeah. And dog tending as well. But that's, I feel like that kind of multitasking is now baked in pretty deep with Pamela. We've got Dave Dickinson. Hey, Dave.
Hey, I'm on Airbnb internet this time, better than hotel internet. So
yeah, your internet looks great. Where are you?
Bristol, Tennessee, right now.
Okay.
Just on the other side of the Virginia border.
So still in
Eastern time,
North America.
Yeah, still in North America. We're kind of putting Spain on hold for various reasons right now, and looking at property around here.
Oh wow!
Exploring.
How are the skies there?
It's pretty dark. I haven't got out outside of town yet, but it's fairly dark from what I can see. Like even here in town, it's not bad.
Yeah. Thanks for muting your mic, Mike. There's definitely a background audio, so I can hear Dave. So just keep that in mind that there's like a background hum when you're not talking and your mic's just going. It's trying to listen to the sounds of the universe. But that sounds great. Man, like living in the country and being have access to those dark skies is just great. And we got some guy, aka Dr. Nick Castle. Hey Nick, how's it going?
Hey, Fraser, doing pretty well. How about you?
Good. And where are you?
I'm in Tallahassee, Florida, where the hurricane went out of its way to avoid us.
That was thoughtful.
It really was. There's actually a local superstition that the research lab here is the reason why hurricanes don't hit Tallahassee. And the fact that hurricanes have hit Tallahassee doesn't dissuade anyone.
Right. Because they would really like a hurricane to hit so they could study it up close. Right.
We study magnets here. I don't know what that has to do with hurricanes, but
I feel like it's a sure. Yes, if you create a hurricane study center, then you are guaranteed to never have a hurricane come anywhere close to you.
Then we should definitely found one in the middle of Florida right now.
Yeah, exactly.
Yeah.
All right. So before we get on to our special guest, I want to give just a huge shout out to our good friends of the Weekly Space Hangout crew. They're our friends, our fans. They call the shots. We do what they say. The executive producers of what we do. So if you want to join this amazing community, go to wshcrew.space to sign up. All right. Joining us this week, we've got Mike Simmons. Hey, Mike, how's it going?
Hi, Fraser. It's good to be back here after a while.
Yeah. Well, I mean, people will probably remember who you are. You've been on the show several times in the past, as well as a regular on some of the virtual star parties that we used to do. And you've always got an interesting project that you are working on. What are you working on?
Oh, boy. Well, how long is this broadcast?
You got about 20 minutes. So
okay, you got 20 minutes. No, I am.
But you've got a new project. I mean, you're famous for Astronomers Without Borders, but you've got a pretty cool new project that you're working on.
Yeah, and it's called Astronomy for Equity, and the idea is that we hear the stars are for everyone, everybody under one sky, but a lot of the things I learned doing global programs over the last 20 years or so is that people can't access the sky all the time. And why does that matter? Because astronomy can save the world, basically. And what I mean by that is that in most places, and I can show you some pictures here as well, they don't have science labs. They don't have opportunities and things like that. And Pamela's just going randomly through some of them right now. And this is, for example, an astrobus in Ethiopia where they brought astronomy to a very rural area. These people have never had a chance to do science. There are students, there are brilliant people in a lot of places. I'm talking with a polymath right now, is a Syrian refugee in Jordan who makes me feel dumb, but what chances does he have? And we try to help them. So it's focusing on that kind of a thing. And I can, let me see if we can show.
I mean, you wonder about that. Like, how many Einsteins are there right now today around the world who could be making a dramatic impact on the field of science, and yet they don't have access to the tools, the techniques, the education, internet, etc. And
exactly, and I would say that
just put the right
probably 10% of the world's population has an opportunity to take advantage of their abilities. So there are 10 times more Einsteins than we know about. The other thing is that a lot of countries just they don't have the opportunity to develop. I was helping get telescopes to Tanzania one time, and a comment was, well, I think they need more, they need food more than telescopes. And that to me epitomizes the short-sightedness, which is that they need scientists and engineers. They need people who are capable of doing these things. And when they get a chance to go to Europe, they usually don't come back because there's nowhere for them to do this. Right now we have a picture of, this is one of my do you know things. This is Iran. This is timely. an educational observatory I visited in Tehran. And this, it turns out that, first of all, astronomy is something that young people do around the world. Not like here, where it's us old white guys, but it is really diverse and really young. Iran, it happens to be 90% young girls, women. And so the sciences are kind of dominated by them. And I can tell you that anybody that riles them up to the point where they're marching in the street is in big trouble. Based on my visits.
So is that an astronomical club in Iran?
That's the observatory.
Like
they are
all women.
Yeah, it's a. I didn't even realize when I visited there, and I looked at the picture later and said, "Wait a minute, there's only one boy." And it's one of my first visits. I've been there a lot of times, and yeah, it's classes. It's like a club, and so now other things. For example, I know people doing astronomy in Afghanistan, which has gotten a whole lot harder now. And there's a good one. This one, okay. I want to show this one and the one after. So this looks like a great little classroom. Of course, they don't have any chairs, but most of the world doesn't. They sit on the floor, and they're having a good time here learning about astronomy. Well, this is a refugee camp. These kids are internally displaced people in northern Nigeria who had to run away from Boko Haram, or these girls in here would have been taken and turned into slaves, and very bad things. And the next one shows, you can see the conditions. And these are just normal people, but they've never had a chance to look through a telescope or anything. And those Einsteins, I've seen here in the U.S. people get inspired by looking through telescopes. And Dave and you guys all know about this. What happens? And they go into science because of that. Well, they need that here. They don't have. There's no chem lab there. I hope, but or biology lab or geology lab or anything like that. But, in a lot of these places, they got a better astronomy lab than we do, because it's dark out there. So we use that for introducing science.
That's a good point. Yeah, that's really interesting that they have a better access to skies than anyone else on Earth, and put the tools in their hands and let them be unleashed by the wonder of the sky. I love that idea. So what do you like? How is this project working? How does it work?
Well, there is an example right there. This is an astronomy club, actually a network of astronomy clubs. It's in Syria. These young people are passionate. There are amateur astronomers everywhere. That's one of the things I've learned, connecting people together. You can go to any country in the world. There are amateur astronomers. They may not have a telescope, but they are doing outreach. These are Syrian girls. Again, it seems to be mostly girls, though it's not only. National organization with a huge following across the Arab world. Ministry of Education support. They've created astronomy clubs in middle schools in 5 cities across Syria. These young people have grown up with war, ISIS, political unrest, and these are things that really inspire them and give them a chance to dream. In this case, though, with everything they have going for them, they can't get telescopes. So we're raising money to get them telescopes. It's a tiny little piece out of everything that's needed. What they have is sustainable, it's scalable, proven organizations. They can't get telescopes. So we're crowdfunding right there.
Can people get involved in this project? Yeah. So how does this work? You're crowdfunding
This is crowdfunding
projects?
Here, so you go there and give us all your money. It actually, I've gotten it as small as $1 donations, and those make a difference because it shows somebody cared enough to give what they could afford. If a millionaire gives $100, it doesn't mean much. If somebody has $1, they give it to you, it means a lot. So any amount really helps. So that's one of the things. another thing that we're starting and people can participate in this. The idea here is to give opportunities to marginalized communities in whatever way. In this case, it's just because of where they were. Other people, they're born blind. They don't see the J-West images. There are captions, there are sound things. They know about astronomy. They're as interested in astronomy as anything else. And, I know brilliant blind people. There are materials like this that have been created by NASA, by Chandra, by Space Telescope Institute, all kinds of resources and expertise in how to do this. But they don't connect with the people who are out there doing it. The big resource is the amateur astronomers everywhere. And I know from going around the world and talking to people, this one's a planetarium program. You listen to it and you feel the dome. Yeah, you guys should know about this, but you don't because there's just this disconnect. So again, it's a small piece for bringing together the experts who do this, who have the resources, and who have done outreach. Outreach groups can join. There is a forum on there that I don't think I put the link in here for outreach groups to join in, and we'll show you how to do it. I just talked to somebody, a young person in Nepal today. They figured out how to do this stuff on their own, but there's no need to reinvent the wheel.
Yeah.
So we got the people out there ready to do it. You just need to connect them. That's the idea. Little things, big return.
So for for people who are watching this and are excited about this idea of helping to connect, where should they go? What's the best way to do this?
Yeah, so these are the two things. We're just starting up now. The website is astro4equity.org. I don't know if I put that anywhere, but that's what it is, astro4equity.org.
Astro4equity.
Yeah, and there's there are a lot of little stories there about people you really wouldn't know. There's kind of a lack of understanding about how difficult things may be, but especially what a big difference these little things can make. These sparks that inspire people that go on to something really great.
Dude, you're underselling this. So let me see if I can take a crack at this for you here. If you want to participate and help get the word out and to help, what these people is they need money. All these different projects, they need access to telescopes, they need access to learning material, and what they really need is money. And so go to astro4equity.org and take a look at the projects that they have running. We've got a profile of what you're doing on Universe Today. Nancy wrote up a story about you guys as well. And get involved, and you'll see the impact that your money is having on the lives of these people around the world. And over time, I know Mike is going to be giving us pictures and showing us the results of people getting access to astronomy. And if you love astronomy and you remember that time when you first looked through a telescope and saw Saturn, and saw Jupiter, that is an experience that everybody can get a chance to have, as long as we can get more telescopes out to more people. So, because you weren't hard selling it, Mike. So there you go.
I appreciate
Participate.
that. I'm just not that type, and I need help. I'm in the wrong business. I need to be out selling. I just want to do stuff, and I like to do things.
You leave a trail of
just a big return on the investment. Yeah, but really, it's since this is a startup. Anybody that knows the word startup, you know what startup. If you've done it before, then that actually puts chills down your spine. But this is using. I've done things like the 100 Hours of Astronomy Global Star Party in the International Year of Astronomy. We spent $30,000 to get 1 million people looking through telescopes in one night. It's because of the volunteers. It's the passion out there. We're just trying to give them the opportunity to do these things, and they're waiting for us. So let me see how I can do this. go to astro4equity.org and give us your bank account so we can empty it out. But
Okay, wait a minute.
honestly,
Created a monster here.
honestly, we do so much with so little, and startup is tough. We've got plans galore, and I'm impatient. I want to get them done.
Yeah, and I mean, your track record is a mile long. You've been doing interesting projects for outreach and organizing astronomers around the world for probably as long as I've been alive. So keep it up.
Yeah.
So if people want to follow your work, Mike, what is the beyond the Astro for Equity? How can they follow you specifically and keep abreast of what you're up to?
I'm not real great with social media, but I do what I can. So Facebook is probably the best, and that's I have a page. I got up to 5,000 friends on Facebook, so I had to create a page so I could have more friends. So now I have two things going on. So if you look for Mike Simmons, and I think it's Mike Astro or something like, you'll find my page, and that's really where I post most of the stuff.
Okay. That sounds great.
But there's also a newsletter for Astronomy for Equity, which is the main thing that you can sign up for on the website. And when we get a few more subscribers, again, we're just starting this new initiative.
Excellent.
You can get on that there, and we'll be talking about, there is a lot more behind all this. I've been talking to Star Trek people, like, real people in Star Trek universe about, somebody had the great idea that Gene Roddenberry's vision of an equitable federation of planets is kind of what we're doing here. And we're doing it by going into space. I mean, I saw a rocket go today, and earlier from Florida, 5 people went to space, but they're 100 miles away from Earth. We astronomers, we explore a whole lot farther.
Yeah. Well, Mike, thank you so much. Thanks for giving us an update, and good luck with your project.
Thanks for having me again, Fraser.
All right, let's move on to the news portion of this show. Pamela, let's see you multitask. And why don't you talk about the globular clusters? Oh, you're muted.
Of course I'm muted. Tradition. So it turns out that these objects that we've been trying to figure out how they form, and we were really hoping that if we looked far enough back in the history of the universe, we'd find baby globular clusters. And it turns out globular clusters appear to have been one of the first things formed, however it is that they actually formed. This result is one that just kind of boggles my mind. The JWST looked at gravitationally lensed galaxies that look just like streaks because of how the bending of the light is not perfect as the light goes through the galaxy. Now, in this bent light, researchers were able to find structures of the galaxy that are the globular clusters. They refer to them as sparklers. And the objects that they found were already old when the universe was 4.5 billion years old. And we think that globular clusters are formed in the shock waves of interacting galaxies or other massive collisions. We've seen a couple instances where that appears to be what's happening. And so the fact that these globular clusters are so old tells us that these were forming at the very beginning of the universe, and it was probably a very violent time. And what I love is this is research where we can't directly look this far back in time. But by combining the power of the JWST with the magnification by gravity in galaxy clusters, we're able to look at, admittedly extremely distorted, but things we otherwise never could see even with the JWST. This coupling is just not something I anticipated would be used the way it is used.
So that stretchy, almost phallic object on the right
Yeah.
is actually a stretched out globular cluster?
That's a stretched out galaxy, and where you see the little tiny box
Yep.
on the yellow outlined image,
Yep.
that little
Yep.
tiny box is the globular cluster.
Got it.
And so
And
in the
so
Hubble image,
lets
we
you
couldn't see this.
Right. That's really cool. Yeah.
Yeah.
And so thanks to gravitational lensing, I mean they're just really scratching the surface with what's going to be possible with these gravitational lenses. The potential that we can even see like the first stars in the universe. So do we have a sense of how old those background galaxies are?
They're all over the place because we're literally finding hundreds of these gravitationally lensed objects. They span all different ages. And what's interesting is there's already debate on how some of the JWST images have been processed, and that's a completely different story. But there's some debate on actually the age of some of the things that are being seen and whether they're as old as people think. The dust hasn't settled yet. There's going to be in December a JWST First Science Results Conference. I regret I won't be able to attend it, but better things are to come. And in December is when I expect we're going to start seeing massive amounts of, well, this is JWST's furthest, this is JWST's youngest of this kind of object that was found at this distance. There's so many firsts waiting to be made. This was the first set of globular clusters.
What is it, January? When the AAS meets?
Yeah.
And I'm sure it's just going to be web. No,
yeah.
It's going to be kind of overwhelming because they've all been doing their science, they've all been doing their research, they've all been sitting on their data. They haven't been sharing it yet.
Yeah.
Apart from some, and now we're going to start to see this. And I love it when we get these little sneak previews, of some of the results. Oh, and here's this thing that almost overturns our understanding of the way this thing comes together.
Yeah.
Yeah, right on.
Yeah.
Cool. All right, Dave, let's talk about the flyby of Juno.
Yeah, last Thursday, NASA's Juno mission, Juno being the only mission that's currently active around Jupiter, made its flyby past Europa. Now, Juno wasn't meant actually for exploring the inner moons, but now that it's done its primary mission, which was to study the magnetosphere and the gravitational field and try to probe the interior of Jupiter from a further looping orbit, they're getting a little more daring with the mission now in its extended mission, going deeper into that radiation field, into the inner moons, the Galilean moons, and they did a flyby of Ganymede last year, and they're doing one of Europa. This is on Perijove, right before Perijove 45, just about 7 hours prior. It passed about 200 kilometers, a little over 200 kilometers from the surface of Europa. And next year they're going to go past Io, which is going to be even a little more challenging. The thing is, Juno has solar panels. Those solar panels are very sensitive to radiation, so it's going to be the inner computer part. The core of it is encased and shielded, but any encounter with the Io Jupiter radiation torus could probably not be good news for the solar panels on it. But they got a little more daring on it.
So this could be its last flyby.
Eventually, it's going to impact Jupiter. They're going to dispose of it by having, like they did with Cassini, like they did with Galileo. Incidentally, the last mission to go by Europa was Galileo in 2000, and that was the last time we got a really good look at it. Europa, of course, is we're very interested in it because it's not. It looks like it's active. It's got ice. It's got grooves. It's got an icy surface. It's the microwave.
There.
Yes,
that's the picture. So that's the picture that came out just about 3 hours ago.
They just released this a few hours ago, and I dropped it in the slideshow right before the show.
Yeah.
And what was interesting, this was from one of the star trackers. This wasn't from Juno camera, one of the primary cameras. It's a black and white image, and they had the star trackers on during its closest pass to Europa. And this was actually when they were in the shadow of Europa, and how they did it. Jupiter is near opposition right now. So it was kind of backlit. Europa, that nighttime side, was backlit by what they call Jupiter shine. Like you think of Earth shine when you're looking at the dark limb of the crescent moon, and you can kind of see it lit a little bit kind of there because the Earth is acting as a mirror reflecting back at it. Jupiter was acting as a mirror during the same point. So the star trackers and some of the infrared imagers from Europa or from Juno were actually able to get some data. The data from the microwave radiometer, when I talked to some of the researchers on it, might be kind of interesting because they might be able to get some kind of fix on the temperature and the thickness of the crust, which is something that we would really like to know on Europa. And this is leading up to Europa Clipper, which is launching in, I believe, 2024. Yeah,
that's right.
Which is coming right up. We're already almost through 2022 right now.
Yeah, and it'll arrive in 2030.
Yeah, so it's going to take a while to get there. But this kind of information will inform the Europa Clipper team for their missions, where they're going to be doing several close successive flybys of Europa.
Yeah, it was. I mean, it's great. I mean, Juno's been amazing, and that they now are using it to take some images of the moons of Jupiter is exciting and brave and reckless.
They did this with Cassini too. Remember, they did the extended mission where they went in through the ring system, and they kind of went in. Like I said, you can be a little more daring toward the end of the mission, where we're not quite as concerned if the spacecraft sustains. And this was the first solar-powered mission to the outer solar system. So the solar panels are huge. They're about the size of a school bus, and it has 3 of them on it.
Yeah, I think it's 1/25th the amount of solar radiation falls on solar panels at Jupiter than it does on Earth.
I remember.
Or is it 1/9th?
I don't have it written down, but the number of watts of power it generates is not. It's like it's not a whole lot. So panels, but it has been quite an amazing mission. I'd like to give a shout out too to all the people that do the volunteer image processing on these. You always see these amazing people are taking the JunoCam images, like Kevin Gill, Jason Teacher, who is a Weekly Space Hangout alumni, Judy Schmidt, that are taking these things and doing some really incredible things. If you look at the JunoCam webpage, that's all volunteer processors that are just taking these things and really producing some amazing images of Jupiter and the moon.
Yeah, it's just amazing. So great. All right, Nick, I choose the solar cycle.
Oh no, he makes me be an astronomer first.
You offered up the story. I want to learn about it.
I know. So, I was looking around for science to talk about today, and one of the headlines was that we just had an X1 flare observed literally 3 days ago coming off of the sun. And that got me wondering, like, okay, let's get a little context to this. Why is this remarkable? Well, X1 is part of the X class of solar flares, which are the most energetic solar flares that the sun produces. And as I'm trolling through this, I'm seeing things like this is way more active of a solar cycle than we'd expected. See, every 11 years, the sun goes from not very much going on to a whole lot goes on, then the poles flip and everything resets back to normal. And you go to the next solar cycle. And apparently, people way smarter at this than I am actually predict what those should look like from cycle to cycle. This is apparently the 25th one we've tracked, which a little math means we've been tracking these for way more than 250 years. Anyway, one of the reasons why this caught my attention was because, well, I've been watching this crazy, scary TV show called The End is Nigh, where Bill Nye comes back with a scary version of science, telling us how the world is going to end. And the 3rd episode is about how, essentially, a good-sized solar storm can knock out our entire power grid. And this got me thinking about, okay, like, how realistic is this worry? Well, the thought is, if you get a big enough event that aims at the Earth, you could knock out not just the things that are orbiting up in space that could be knocked out by this directly, but you could actually create flow of current in large conductors on the surface. Things like, I don't know, power grids. And there are ways that we can harden this, and
Internet
perhaps we should.
communication networks.
But one of the big things is we don't have all of the science details of exactly how that solar event impacts the Earth. And this is where NASA is actually coming forward and saying, well, let's study that directly. So they're talking about a new constellation of satellites called, I'm going to mess it up, so I'm going to look it up. The Geosystem Dynamical Constellation. Yes. Geospace. Sorry, I'm so close. And this is a constellation of satellites. It's several that are going up to look at the thermosphere and the ionosphere, which are two of the outermost layers of what you could broadly call atmosphere. Not the kind of stuff you can breathe, but the near-Earth space environment. And figure out, well, what really happens when solar flares hit the Earth's magnetic field by doing in situ measurements to really deeply characterize this environment. I'd never even heard of this mission, so finding out that this stuff that keeps coming up in just popular media, I'm now seeing and here we are in the solar cycle, so right now is maybe when we should be more worried about we haven't prepared for this, and hey, look, we're going to study this. It was just a cool connection.
Yeah. It's, people ask me should we be worried about asteroids? And the answer is not really, right? The chance of a bad asteroid actually striking the Earth during our lifetimes is quite remote. Yeah, sure, we could have a city killer show up, a Tunguska every few thousand years or so, but you don't have to really worry.
The one that scares me is the Oumuamua. This just came in from
Sure.
our solar system on a high-speed
Yeah.
trajectory. We didn't even catch it until it would have already nailed us.
Sure, but again, the chances, we don't have, the Earth isn't littered with smoking craters of comet impacts.
Or is it?
Or a black hole coming too close to the solar system. Well, you're the geologist.
Well,
Tell
it
me,
takes some time.
are there many comet impacts that have happened in the last 100 years that have wiped out big chunks of planet Earth? Because if there have,
Whoa.
haven't
You're
noticed.
confusing a few things here. I'm a geologist. 100 years is no time at all.
Yeah. I'm saying like risks, right? And so then what else do you got? You got gamma ray bursts again, supernovae, not a real big problem, but a coronal mass ejection is inevitable. We've seen them happen every few decades that could cause significant damage. And the more we plug our computers into each other, the more dangerous. The more we plug our houses together with wires, the more dangerous this comes. And not any effort is spent to think about how to protect ourselves. So that is the scary one.
The Carrington super flare was in 1859. Yeah, it wasn't that long ago.
No. And we've seen ones that are worse that just didn't hit us.
Yep.
We've seen ones that have been far more dangerous than the Carrington one. They were just going in away from the Earth as opposed to towards us.
It said telegraph offices on fire. It was kind of interesting to read accounts of it. That was the high tech of the day. So,
people saw auroras at the
down
equator.
To Puerto Rico and places that never.
And that's actually the kind of stuff that this scenario paints as being so scary. It's not just we'll lose power for a few days. It's the power grid itself will surge with so much power that critical components will die, which means we can't actually power factories to replace the components. And congratulations, we're back to the Bronze Age.
Right. Yeah. So because everything is connected into one big circuit, then you get a failure at any point and the whole thing goes down. And what you really want is you want things to be modular and redundant, where one little microgrid can go down, but then your neighbor can just walk over and plug you in and give you some power. So
you also really want hardening of the critical failure points, so that first off, there's a detection of, is this kind of surge happening? If so, immediately and automatically disconnect. Then the physical infrastructure to say, okay, if there was a surge coming, how would we stop it from destroying the thing? That kind of stuff.
Yeah, and it seems like such a nebulous, hard to wrap your mind around risk, and yet it's almost inevitable that we're going to have a extreme event. We had the one in Quebec back in the late
Yes, back
80s.
in the 80s.
Yeah.
Yep.
Yeah,
Starlink,
and that was
Starlink lost a batch of satellites
Yep.
earlier this year to a solar. It just was
Yeah.
bad timing. There was a solar event right when they launched.
And the solution to this problem is also actually good for other things too, like
Yeah.
breaking up the grid, generating your power close to where you live, not being so reliant on these big long transmission lines, etc. This is all good. Like this is all would be better for our modern grid. You see places like Texas when the whole grid goes down, because it's all interconnected and has so many points of failure. Yeah, where's this End is Nigh? Is that on Netflix?
It's actually on Peacock.
Huh, I haven't even heard of it.
No, I haven't heard of it.
Yeah. All right, let's move on. Pamela, let's talk
Razor.
about 68 new gravitational lenses.
So I hinted in the prior story that gravitational lenses are really becoming how we explore our universe. And the way the gravitational lenses work is you have a large bundle of mass that exists between you and whatever it is that you're looking at. And light that is coming past this mass of stuff that otherwise would go to some other part of the universe is getting bent by the mass. And this mass is acting like the world's worst magnifying glass because everything is distorted. But it is allowing us to see so much more light that normally would have gone elsewhere. Now, trying to identify gravitational lenses in images of galaxy clusters can be exceedingly difficult because galaxies come in a lot of different sizes, colors, shapes. And so we've had to train software because there's more images than the humans can deal with. We've had to train software to look at these galaxy clusters and identify streaks that are arcing around the center of mass, essentially, or a different knot of mass, essentially, in the system. And a team led by Kim van Thrain has identified 5,000 candidate gravitational lenses. They haven't gotten telescope time to follow up on all 5,000, but they did get telescope time to look at 77 candidates. And of those 77 candidates that the software found, 68 were confirmed to be gravitational lenses. Now, what's amazing about this is we can use gravitational lenses to start to measure the geometry of space in an independent method from everything else we're doing. And one of the trickstery things about this is, if you have a large mass and it's lumpy and it's bumpy and there's something behind it, that something that's behind it might get bent into an image that you see up here, and it might get bent into an image you see slightly beside it. And these multiple images, the light has been traveling for different distances. It's just a triangle. It's a bent triangle. It's more complicated than that. We're going to call it a triangle. Cows are spheres. So you have these bent objects.
Imagining a spherical cow.
You're imagining a spherical cow. The spherical cow is the giant thing of mass that is bending the light. And this one light path might be very long and the other one might be slightly shorter. And that means if there's something in that background galaxy that flickers or flares, an active galactic nuclei doing something interesting, we're going to see that flicker and flare in one of these distorted images, the one that took the shorter route first. And then later we'll see it with the one that took the longer route. And by knowing those distances by light travel time, we have an independent way to get at the different distances and start measuring the expansion rate of the universe. And their software is working. Their software has 88% success rate. They have 5,000 targets to look at, and they're going to have even more once we start getting the Vera Rubin Observatory on. And I'm super excited about this because we can't currently accurately measure the expansion rate of our universe using different methods, and having a third method might finally tell us which of the two methods we currently use is wrong, or if both are wrong.
I mean, I love this idea that you can just feed this mass data into the computer and it's able to identify potential gravitational lenses. And it seems it's like what, 88%
88%
accurate or
success rate. Yeah.
yeah, and so I mean, you mentioned in the story there's like 56 of them or something that they've confirmed visually.
They confirmed 68 of 77.
Right. But there are another 5,000 that the computer's going, here you go. Whenever you're ready, take a look through these, which is really exciting. And I mean, I feel like this was the hope for the longest time, that finally computers can step in and you can just throw the entire night sky and say, hey, computer, find all the gravitational lenses. Hey, computer, find all the whatever, right?
We're starting to get there. They're super faint, and these are being drawn from the Dark Energy Survey and the Dark Energy Camera Legacy surveys. So these are in a lot of ways precursor surveys to what Vera Rubin is going to do with the LSST. And so we can see the potential, we can see that the machine learning can be trained accurately. And once we start imaging the entire sky every 4 nights as seen from Chile, it's just going to increase and increase the number of these that we have found. And some of these gravitational lenses are going to be some of the first galaxies forming. These are targets to be followed up with, in some cases, with JWST. This is super exciting work done from the ground. We don't get enough of that.
Yeah. So exciting. Very cool. All right, Nick, we've got one more story from you. Let's talk about Ryugu from the outer solar system. What?
Yeah. Ryugu is a near-Earth asteroid. It's one of the reasons why we actually, by we I mean humans, because it's JAXA, not NASA, sent a spacecraft there to visit it. Near-Earth objects are easier to get to than many, many other things. But this one appears to have migrated in from possibly even further out than Jupiter. Now, we know that Ryugu isn't the primary asteroid. It wasn't what formed originally. It would have been a larger object, got hit by something really big, blew off a lot of pieces that then came together and made this sort of rubble pile. I think we've known that for a while, and we knew that it was dark and had the right kind of spectral features for us to say this is probably related to carbonaceous chondrites. As we got really close to it and saw more detailed spectroscopy, that just helped confirm that spectroscopic imagery. But to really nail down what this thing is, we really wanted to take a sample into a lab where it could do many other kinds of analysis that weren't just spectroscopic imaging. And so they did that. And they actually took in, there's a group that studied, it was 17 different, they call them particles. These are little tiny grains. The largest one was 8 millimeters on axis. There's actually a picture in my slide deck of it. And then they not just took that 8 millimeter object, they sliced it into little serial slices and made what amounts to a geologic thin section of each of those slices and analyzed it. It is absolutely amazing what they pulled off with this. But the cool headline that they pulled out was, first, to confirm, it's a carbonaceous chondrite, specifically of a class called CI chondrites, which is one of the subclasses. It's not a very common one. They compared against several different other meteorites we have of that. And they compared it against things like the Tagish Lake meteorite, which is one of the most pristine ones we have from the ground. But these samples had never been exposed to air at all, ever. And so they could look at things that were like little fluid inclusions in some of the mineral grains, say, what's that? And what does it tell us about the formation of this? Because we know it's not Earth contamination. And they found evidence for liquid water flowing around this. They found evidence for carbon dioxide ices having formed at one point in time. And all of this comes back to a formation environment that had to be colder than the entire inner solar system. So they're really looking at something that had to have formed out past Jupiter. Now, one of the reasons why this has me so giddy and excited is because Jupiter is one of those big bully boundaries that we think happened in the early solar system where stuff tries to cross it and Jupiter says, nope, mine, doink, and I eat it.
Mm-hmm.
So moving stuff from the outer solar system to the inner solar system is hard. And so having a hand sample of the outer solar system, we can learn so much from that. Anyway, so this was published actually just a few days ago, I think a week or so ago. And so just seeing these results come out, by the way, you should look up this paper on Science. It's Nakamura et al. There's like 180 authors. It's absolutely insane. But their data set is a tour de force. Like everything I could have thought to apply times 5 was done to these little tiny dust grains.
Yeah.
All right, bigger than dust, but little tiny grains.
So how did it get there then? If it came from the outer solar system, how could it have migrated that far into the inner solar system?
That sounds more like a Pamela question than a Nick question.
I guess.
I mean, ultimately the answer is probably things hit each other hard enough to change their orbits enough that it skirted past Jupiter.
Yeah. Yeah, I mean, that's the question. I think Jupiter's there.
It's not generally a very stable place to be unless you end up in one of the Trojan Lagrange points where they hang out. The Centaurs...
Or in orbital resonance with Jupiter. That means that essentially Jupiter misses you a lot.
So there's a few sweet spots where these objects can hang out in the outer solar system, but none of them are stable. And over time, we see objects getting flung inwards and outwards that go both directions. And it's through these gravitational instabilities that things migrate closer and closer to us in some cases. The asteroid belt itself has basically bands of stability that are caused by all of the inner and outer worlds tugging in different ways. Migration is something that just happens. Yeah. It happens on hundreds of thousands of year timescales. But we've been around as a planet for 5 billion years, so that's nothing.
When we got our brief view of Didymos last week, the first thing I thought is like, it looks like Bennu and Ryugu. It's a rubble pile just as simple.
Yeah, that sure looks familiar.
Yeah.
Yes.
It was a little more egg-shaped than diamond-shaped, I thought. But yeah, it's a rubble pile, which is debris from these big collisions.
So are they all rubble piles?
No, because we've seen Itokawa, which is a similar shape and similar size. And Itokawa was...
It was bigger, though, wasn't it?
It was similar in size, I believe, to Ryugu and Bennu. I could be wrong, but it was very much a cashew with rubble on it.
Yeah.
So in some cases, you can get cashews with piles of rubble. Sometimes you just get rubble all the way down. And the more of these we see, Eros is another one that we have close-up images of. It is significantly bigger, but it's another one that had nice, smooth, appears to be differentiated and stable surface areas.
I just searched Google for Itokawa, and there's a little 3D version of the asteroid that you can interact with, which is highlighted with different scientific findings.
Can you drop the link into chat?
Just search for Itokawa on Google. Let's see. Like maybe it just happens only for me.
Well, we're gonna have differently.
I don't know. See if you
see it. Solarsystem.gov. I think I got it.
No, if you just search for Itokawa, it's baked into Google. Oh, it's over on the right hand side for me. It's like in the right hand side. There's like a little card that talks about Itokawa, and then there's a 3D model, and then you can click it.
This?
Yeah. Yeah. It's essentially that. Yeah. But the one on Google, has little spots on it that show that it has a weird lack of impact craters, shows where the touchdown sites were, that has 2 lobes of divergent densities. That's really cool.
It looks a little more
Oh.
like Aircoff, kind of, in a way.
Yeah, that's
Or
really neat.
67p kind of has that double lobe kind of thing.
Yeah, so if I search for Comet 67p, hope everyone's doing this as well. Nope, that one, just Itokawa. So I guess because you found that 3D model, Pamela, they must have slurped that in and displayed it on the page. That's really cool. All right, well, you know what? We've reached the end of our hour, so it's time to wrap things up. I'll let you all Google this for yourself. This is your homework. Find how many 3D models of asteroids you can find.
If you're
Dave.
looking for 3D printer ones, there are a lot.
Yeah.
Oh yeah, maybe you can go and 3D print your own asteroid. The 3D printer tech is apparently these new resin printers.
They're
are the
really
bomb.
good.
Yeah, they're the way to go. The ones that melt the plastic are just so finicky, but these new resin ones are apparently. I kind of want one. Anyway, and then you can print little figures for your war games. Anyway,
they're
all right.
amazing.
Yeah. Dave, what are you working on, and where can people find out more?
I am a frequent contributor, Universe Today and Sky and Telescope. I am the author of our recent Deep Sky Astronomer's Field Guide and the Universe Today Ultimate Guide to Observing the Cosmos. Both are on Amazon. And I am at AstroGuys with a Z on Twitter. And right now we've been kind of trying to track Blue Walker 3 that we talked a few weeks ago. There's discussion about that it might have unfolded, but AST Space Mobile, there's nothing from their account. I've seen some people say that it's really bright. I tried to watch it. We have a series of North America passes, so a bunch of us have been trying to verify. I didn't see it last night, but some people have claimed that it seems to be Schrodinger's satellite right now. It's both open and not open right now. So
yeah. I mean, if this does what they're threatening to do, this is the space disaster that everybody was worried about.
We think it may be as bright as the ISS.
It could be as bright as Venus, and there could be a constellation of them.
They want to do 120 of them, yes.
Oh, this is a nightmare. This, Starlinks, you can just barely see them when they're raising altitude, and
I might
you
have
can see them in a telescope.
I might have 5G sat phone connection on my phone with no intermediary. So who knows?
Using your blue shift or whatever it is.
Yeah, who knows? But
yeah,
we're trying to track it, so it's interesting to see how bright it actually is.
Nick, what are you working on, and where can people find out more?
I'm working on way too many things that sadly you can't find out much about any of them. But I am the Wandering Scientist. You can find me on Instagram and Twitter infrequently. But send me something and get my attention.
Awesome. Pamela.
I can be found as Starstrider just about everywhere, spelled with a Y, because I made strange choices in my 20s. And when I'm not tweeting or writing articles on Medium, I am one of the co-hosts of the Daily Space, which goes out on YouTube on the CosmoQuest X channel and on Now Media on Saturday and Sunday nights. And when I'm not doing that, I'm with you, Fraser, doing Astronomy Cast.
Next episode on Monday.
Yep.
All right, and of course, I am the publisher of Universe Today, so check out Universe Today on all the things, and we will be back with you next week. Thank you to Nancy Graziano for organizing everything behind the scenes. Thanks to everyone watching us on YouTube and on Twitch. Thanks to all the moderators as well. Thank you to Pamela for both being a co-host and the engineer today. But I don't think we even noticed that you were multitasking. It was that smooth. Thanks to the rest of my co-hosts, our special guest, Mike Simmons. We will see all of you next week. Thanks, everyone.
Bye-bye, everyone.